Hello everybody, welcome to lab 5 of artificial intelligence. In this lab we will focus on the minimax algorithm and the alpha beta pruning. So before we step into the pre-lab, in-lab and the post-lab, let's have a brief overview on the minimax algorithm. Minimax algorithm is a recursive or the backtracking algorithm in order to make decisions, or it's a decision making process and the game theory. It normally uses the recursion to search through the game tree. The minimax algorithm is mostly used for playing games in AI such as chess, checkers, tic-tac-toe, Go and various tau players game. This algorithm computes the minimax decision tree for the current state. Normally in this algorithm there will be two players. One is called as max, the other one is called as min. We also call them as maximizer or minimizer. Both the players fight it as the opponent player gets the minimum benefit while they get the maximum benefit. So both the players of the game are opponent of each other, where the maximizer will select the maximizer value and the minimizer will select the minimized value. This performs a depth first search algorithm for the exploration of the complete game tree. The minimax algorithm proceeds all the way down to the terminal node of the tree and then backtrack the tree as the recursion. Coming to your pre-lab, we need to write the complete workflow of the minimax two-player game. So in this example, see, we have the maximizer at the low level, the minimizer at the next level, the maximizer at the low level, and then the terminal node. So for this pre-lab, you have to traverse from the root node using the depth first search algorithm or the search process and reach the terminal node. And there, if you clearly observe, here for h you have -1 value and for I you have the 4 value. So for the maximum value we normally consider the -infinity, and for the minimum value, minimizer value, we consider it as positive infinity. When you reach this h value, you calculate the maximum, because the role here is the maximizer role value. So in this process we need to compute the you need to present the workflow of the minimax for this two-player game. This is one pre-lab. Then the second pre-lab depends on a variation of the minimax algorithm, which we normally call it as the alpha beta pruning. This is an optimization technique for the minimax algorithm. As we have seen in the minimax search algorithm, the number of game states it has to examine are exponential in depth of the tree. So we cannot eliminate the exponent, but we can cut it to half. Hence there is a technique by which, without checking each node of the game tree, we can compute the correct minimax decision, and this technique is called pruning. This involves two threshold parameters, alpha and beta, for future expansion. So it is called as alpha beta pruning. It is also called as alpha beta algorithm. This pruning can be applied at any depth of a tree, and sometimes it not only prunes the tree leaves but also entire subtree. The two parameters can be defined as alpha, the best, which we call it as the highest value choice we have found so far at any point along the path of the maximizer. The initial value of alpha is -infinity. The best lowest value choice we have found so far at any point along the path of the minimizer. This is the value assigned to the beta. The initial value of beta is positive infinity. The alpha beta pruning to a standard minimax algorithm returns the same move as the standard algorithm does, but it removes all nodes which are not really affecting the final decision but making the algorithm slow. Hence, pruning these nodes, it makes the algorithm faster. Condition for alpha beta pruning. The main condition for alpha beta pruning is alpha should be greater than or equal to beta. And the key points that we need to consider for alpha beta pruning is the max player will only update the value of alpha, the min player will only update the value of beta. While backtracking the tree, the node values will be passed to upper nodes instead of values of alpha and beta. We will only pass the alpha beta values to the chain nodes. So we need to focus on these two things while we are working on the alpha beta pruning. This last but one step and the penultimate step. So based on this alpha beta pruning, the second lab, asks for the complete workflow of the graph by using the alpha beta pruning. So these are the two pre-labs which you need to do before you step into lab 5. Coming to the in-lab, we need to write down a Python code to print the root node by using the minimax algorithm. For this example, after applying the minimax algorithm, the root node value is 5. I'll try to explain this with the pre-lab example. See, in step 1, consider this as an example. This is the game tree that's completely provided. The initial value of the maximizer is considered as minus infinity, and the initial value for the minimizer is considered as the positive infinity. So after defining these two initial values and based on the game tree that's available, let's start traversing. Step 2. We follow the depth search process, and from the root node, that's A, we move to the node H. So that's no. After that we cannot further move. So we need to compute the at this level 0, level 1, level 2. At this level, it's the role of the maximizer. Here you can clearly understand. See, we first find the utilities values for the maximizer. Its initial value is minus infinity. So we will compare each value in terminal state with initial value of maximizer and determines the higher node values. So for this D, we will initially compute. So according to depth first search, it initially reaches this. The minimum value, the initial value of the maximizer is minus infinity. So and the H value is minus 1. So we compute the maximum of minus 1 and minus infinity, and based on that we also next consider. So here the minimum value, maximum value is minus 1. Next, when you move on, backtrack and then move on to the right path. So at right we have I and its value is 4. So now we compute the maximum value of minus 1, which is obtained from the previous step, and the i's value, that is 4. So the maximum of these two is 4. This value is assigned to the D. So once the D node value is computed, you backtrack and then move on to the right part of it. So at this we have the node E. At node E we have the J value onto the left and K onto the right. So again apply the same process. So for node E we have apply the maximizer, maximum of 2 and minus infinity, which is 2, and if you move on to the right, the obtained value is again passed on to the maximizer along with the K value. So the maximum of 2, 6 is equal to 6. The same process goes for node F and node G. So for node F we get the maximum value as minus 3, and for node G the maximum value is 7. See, these values are assigned over here. So all these are the maximizer values: 4, 6, minus 3, 7. This is what step 2 is. Coming to step 3, we go to the next level. This is the minimizer role. So it's the turn for the minimizer. It will compare all nodes values with the positive infinity and will find the third layer node values. So we'll apply the same process, but we will follow the minimizer process. So you backtrack, you will be at B. So minimum of what? This value and the positive infinity. So the minimum of this value and the positive infinity is initially 4, and then when you move on to right, the minimum of 4 and then 6 is 4. So for node B the minimum value is 4. And coming to node C, if you backtrack, so here the minimum value is computed as the minimum of F value, that is minus 3, and the positive infinity, which is minus 3. Then if you consider the right value, it is minus 3 and the value of Z, which is 7. So the minimum value is minus 3. So this is, so at the end of step 3 what we have 4 for the value of B for B node and minus 3 as the value for C node. Now moving on to the next level, it's a turn for the maximizer, and it will again choose the maximum value of all nodes values and find the maximum value for the root node. In this game tree there are only 4 layers, so we can immediately reach the root node. But in the real scenarios we can have more number of layers. So if you consider here it's the role of the maximizer, if you clearly observe over here. So the A's value would be initially the minus infinity. So onto the left you have B value, which has B node, which has a value 4. So you compute the maximum of the positive minus infinity and 4. So 4 you get the value. Then on to the right you have another node, that is C with the value minus 3. So the maximum 4 comma minus 3, which is 4. So the root node value is 4. This is the process that we need to develop using the Python programming. This is what the in-lab is. So to accomplish this, we need to consider the scores at the leaf level. If you clearly observe the leaf level values, those leaf level values will be stored as a list. Next, it also depends on the depth of the tree, which is based on the number of scores. In this example, we only have 0, 1, 2, 3 as the depth. It may go in real life scenarios, then depth can increase. And what is that you are going to return is, we need to return the optimal value. That is the final value that is present in the root node. So that's the goal of this in-lab. And coming to post-lab, we need to apply the alpha-beta pruning, which I have explained in the previous slides. So based on that process, we need to find out the best value of the root node, print the result, and number of pruned times using the alpha beta pruning. So for this example, the output you get is alpha beta values would be 5 comma 15, the result would be 5. The result 5 means this one, the value of this node, and the number of nodes times that are pruned, it is 4. So what alpha beta pruning basically does is, it will not evaluate all the nodes. Based on the alpha beta values, certain nodes will be pruned. So this improves the efficiency of the min-max algorithm. So with this we come to the lab 5 exercise.